benefits of like focusing over
Okay. All right, guys, bring it back, here we are. All right, so half-life, we just discussed, this is how long it takes for 1/2 of the concentration to disappear. So the formula to calculate the half-life for a first-order reaction is incredibly simple. It's 0.693 over K. And so the time it takes for half the concentration to disappear is this formula right here. So this is going to be a certain amount of time. Okay? Mm-hmm.
Are we doing integrated rate laws for like second order?
Yeah, but after the first order, once you guys, I've explained it once, it takes no time to explain the second order one.
And half-life for like second order.
Mm-hmm. It'll be different. So in that case, then let's take a look at the example that we have. So if this is our formula, looking at now number 4 on our sheet that was handed out. Okay, number 4A. So number 4A, we're talking about a reaction that has a half-life of 20 minutes, and it's asking us to calculate K for this reaction. And so take this as a note, guys. You can calculate the K of a reaction simply from its half-life. Okay? So in this case, then, our half-life is 20 minutes, and that's going to be 0.693 over K. And so you just solve for K. It's pretty simple. Okay? So then solving for K, you would end up getting 3.47 times 10 to the negative 2. And because this is K in its first order, what are the units? We want to say that, but what's the minutes? What's the time? The time's in minutes, so it's going to be minutes minus 1. If we wanted it to be in seconds, we'd have to multiply this by 60. Okay? So make sure you guys are paying attention to whether they're using minutes, hours, or seconds, because it will change your units. Okay, for part B. All right, so for part B, if the reaction is 75% complete, so we're looking for how much time it's required for this thing to be complete 75%. So there's 2 ways we can do this. We can do this conceptually and go over the concept that we just learned, that if you do 2 half-lives, you've done 75% of your original is gone. So what would 2 half-lives be? If 1 half-life is 20 minutes, then 2 half-lives would be 40 minutes. Okay? That's one way we could go about solving this. Okay? But not all these problems will be that easy. So there's another way that you can think about it. So the way I want you guys to look at it this way. So we're going to use this equation now. ln of original concentration over current concentration equals K T. Okay, this is the one of the variations that we learned of the integrated rate law. So here's the deal, guys. This is the way I'm going to set it up. I'm going to do, if the initial concentration, we're going to call it 100% because we have 100% of the reactant. After 75% is used, how much remains? 25%, right? So that means that if we had 100% of our initial, after 75% is used, we have 25% or 0.25 in decimal form. So that's the way you can set this up. And actually, it's not going to be concentration anymore. It's just going to be numbers. Okay? And the reason I can set this up is because I know that, okay, if this is 100% of my starting, I've used 75%, so I have 0.25 remaining. That concept is big. Okay, so does that make sense? Any questions? No? Okay, so that's going to be then equal to my K, which I figured out what my K is, so I'm going to plug that in. 3.47 times 10 to the negative 2 minutes minus 1, and then T. And then I can go about solving for T, and T will end up being 40 minutes. Okay, questions how we arrived at that answer? It's super, oh yeah, go ahead, Aline.
Where do you get the 0.693?
That's just the derivation of it's in your book. If you want to follow the steps, it'll break it down for you. I know. I'm doing like the shorthand version of notes just so we get through everything today. But yeah, it breaks it down for you in the book if you want to look at it. It has to do with these and these being half of each other, and then you just solve for what will be on top every time. Go ahead.
Are the rates for half-life always constant no matter how many times it occurs?
No, the rate slows down. Yeah, which is why we see this happen. Because if it eliminated as quickly as the first half did, then you'd be gone in no time. All right, so there's that. Okay, so I want you guys to try number 5 using trial 1 from number 3. Okay, so it's trying to figure out how long it's going to take for 80% of that reaction to happen. So using the data for trial 1 from number 3, I want you guys to figure that out using the half-life equation. Okay, so this is on you guys now. Okay, the level of chatter tells me that we're done with number 5. So for number 5, let's see. Bailey, tell me how'd you set up number 5?
Okay. I used how you did it in part B. So I put ln of 1 over 0.2, because there's 20% left after the equal. And then I set that equal to...
Shh, guys, come on.
I set it equal to the t-value of 0.0133 seconds remaining.
0.013.
I'm still doing how I solved it.
Okay, minus 1. And then solving for t. Okay, raise your hand if you set your problem up like this. Hmm? Yes? Okay. Do you guys, where is this 0.2 coming from?
0.8.
Right, so we used 80% or 0.8 of the reactants. So if we used 0.8, we have 0.2 remaining. Okay, that's why we can do this. Okay, so plugging this in, we get 121 seconds. Raise your hand if you also got 121 seconds. Fantastic. Okay, questions how we did that? Okay, again, I got the K value from number 3 we had already figured out in number 3. Okay? Okay, great. All right, so that's first order integrated rates. Not too scary once you slow down and use them. Okay, it's mostly just plug. All right, so now we've covered first orders. Now we're going to cover second orders really quick. So for second orders, here it goes. Okay, guys, so here it comes. The integrated rate law for second order equations ends up looking like this. Okay, so it looks a lot like our previous problem for the first order. This was the ln of the concentration, and now it's just 1 over the concentration. The previous one had a negative k, and this one is just positive k. And the previous one was just ln of the initial concentration, and now it's just 1 over. So really just substitute the ln's for 1 overs, and then make the k positive. Okay, so it's very similar. Just like this one, or just like the last one, this one agrees with the point slip formula, or not point slip, but y equals mx plus b, where this would be your y, this would be your m, that would be your x, and this would be your b. So if we are graphing this, the graph of 1 over concentration of A versus time is linear for second order equations. Okay, so if you're going flat out from data and you graph 1 over concentration over time and that data turns out to be a linear line, you know it's confirmed you have a second order reaction. Okay, so you're really looking for what's going to be linear, and that will tell you what order you are. So from there then, if you guys note, our slope would be equal to k of that equation, so it's no longer negative k, it's positive k. And then the half-life for second order reactions is a little bit different. So the T1 half is equal to 1 over K times the initial. So now we need to use K and the initial concentration for the half-life. So that's all I'm going to lecture on second orders. So we're going to use it now. Mm-hmm.
Are we supposed to memorize all these?
Yes. But they're really easy if you think about them in terms of y equals mx plus b. If you think about them in terms of this, the m is always going to be correlating to k, either positive or negative. X will always be t. And then your y-intercept will always be either ln of a or 1 over a. And then the y will always be 1 over a or ln of a. It's a repetitive formula. So once you have one memorized, you can really get to the other ones pretty quickly. Or maybe it's just that I've seen them enough in my lifetime that I think that's easy. It's probably that one. Okay, sorry guys. Put them on flashcards. You did all the derivatives for calculus. You can do this one, right? Okay. All right, yeah. Okay, so guys, take a look at the next page of our fill-in notes. We're going to practice with this. Okay, this is cool because it shows us what the graph would look like for both types of manipulations. So if you guys look, we have a table and we've got two graphs. So we're going off of some data from a reaction. And if you guys look, the first graph, that's natural log of the concentration. And is that linear, the first graph? No. So we know that this cannot be a first order reaction. And if you look at the next graph, that's the graph of 1 over the concentration. And is that linear? Yes, so we know that that tells us that's a second order reaction. Okay, so that's the data that will confirm first or second order. So that actually is your answer for A, for number 1A. Oop. All right, so again, there's your answer in words. Our graph of 1 over concentration versus time is linear, so that tells us that we've got to be second order. Okay, on to B. So the differential rate law, if things are second order, remember guys, differential rate law were the rate laws we were finding yesterday. So in this case, the rate is going to equal K times our reactant, C4H6, and then if it's second order, what do? Put a 2 up here. Okay, so that's the differential rate law. We know those. And then the integrated rate law is pretty simple. We're just going to plug into our integrated rate law over here. So it would be 1 over the concentration of C4H6 equals KT plus 1 over the initial C4H6 concentration. Okay. So, and then in order to find the rate constant D, so the rate constant, so that would be K. So to solve for K, we can just plug in a couple things. I'm lost. I think I lost my answers to this. Oh, no, I didn't. Okay. So in this case, we can find the slope, which is equal to K. And again, our slope is the change in Y over the change in X. And so I always use the first and last points on the graph, but it's really up to you guys. You can use any points you want. So in this case, guys, what is our Y values going to be in the table? Is it going to be the 1 over or the ln values? The 1 over, right? Because this is second order. So you want to ignore the ln values and use the 1 over values for the Y's. So my first point then that I would use would be 418.
418
41 minus 100. And then 620 minus 0 seconds. Okay, and that gets us 614 times 10 to the negative 2. And that's going to be second order, so m minus 1, s minus 1 units. So now I have my k. And then finally, we can do the half-life. Am I going too quickly? No? Okay, so my half-life is going to be t 1/2 is equal to 1 over my k, which I just figured out. So k goes here, 6.14 times 10 to the negative 2. Times the initial concentration of 0.1000. And so my half-life is going to be 162 seconds. And that's it. Pretty simple stuff. Okay, really, most of this chapter is just plug and chug. I think the hardest part about this is just figuring out like how to read the problem so you know what equation to use and what variable to solve for. But really, after you've got that figured out, it's pretty simple. Oh yeah. Oh no, everything is assessed about this chapter on the AP test. There's one thing in this chapter that you don't have to know, and it's the mathematical application of the Arrhenius equation, which is what we're learning tomorrow. Yes, we're learning the concept behind the equation tomorrow. But you all want to come in on Saturday, don't you?
Excuse me?
We'll learn on Tuesday. Okay.
No one contradicts me. Like, does he want to make it? Okay, so. Because you know I'm going to go off. Anyway, so, we're live, right?
Okay. Are we still working? Okay, so guys, here's your answers for 1 and 2. So this is your differential rate law at the top. It's second order, so we just write the rate with the 2 on top. Raise your hand if you got that right. Fantastic. Number 2, we just plug it into the the integrated rate law. And then for 3, for part C, remember guys, the slope of the graph of 1 over the concentration versus t will give you the k. So that's what we have to do in order to figure out the slope, or to figure out the k. So what I'm going to do is I use the column of 1 over concentration as my y and t as my x to figure out my delta y, delta x. And so I just plugged stuff in. So I just picked the first and last values like I did before in my other examples. And then my k, I get 0.0600. And this is m minus 1, s minus 1. Make sure you guys are paying attention to units. That's stuff that you easily lose points on. Raise your hand if you got that as the k value. Okay. And then lastly for D, guys, the half-life, t minus or over 1 equals 1 over k times the initial concentration of C4H6. So knowing that, we just plug it in. So our k was 0.0600 times the initial concentration was given to you. Just look at T0 and look at the concentration column, and that's 1.0 times 10 to the negative 2. And we end up getting 1.67 times 10 to the 3rd seconds. Raise your hand if you got that as your answer for D. Great. Okay. So, questions before I move on from this topic? Go ahead, Aline.
I don't get which graph
So remember, we want to use the graph that gives us the linear line, right? So the one that's going to give us the linear line is going to be the 1 over concentration versus t. Okay, so you have to use the slope of whatever's linear, and that's why we have to use it. Okay? Okay, guys, one last thing to learn before we go. It's literally like 7 lines of things to write down, and then we're done. Okay, guys, really quick. You won't see these very often, but for a zero-order integrated rate law, you have the concentration of A is equal to negative KT plus the concentration initially of A. Okay, so it follows the same format where you've got the A over here at a specified time, and then negative KT, and then plus the initial. I don't remember what I was going to say there. Oh, this follows the same format too. Y equals M X plus B. Okay, so this means that if you plot your concentration versus time and it's linear, you have a zero-order reaction. Okay? Your slope for this kind of thing of that graph would be equal to your negative k value. And the half-life for these problems are okay, so that's all you have to know for zero orders. More just plug and check. So there's that. Okay.